So this will be the fourth lecture out of chapter 19 over amines, and so this will be the last chapter, the last lecture. So in this lecture, we'll look at this concept of using amines to make diazonium salts, so the nitrosation of amines. So if you take an amine and react it with sodium nitrite, NaNO2 and HCl. So this is the basic mechanism what happens. So this is nitrite. If you drew its Lewis structure. So what we're going to do with HCl is we're going to protonate nitrite to give this, and then we're going to do it again. So take a lone pair of electrons on oxygen, make a bond to hydrogen, and now you have this. And then what's going to happen is a water molecule is going to leave, so take those 2 electrons with it, and now you have this NO2 plus electrophile, and that's what's going to react with your amine. So now we can bring the amine in. So take our amine and take a lone pair of nitrogen and make a bond to that electron deficient nitrogen. And so now nitrogen's positive, and then lose a hydrogen, so lose H plus. Where does that H plus go? That H plus goes with the chlorine that you had in the first step, so you make HCl as a side product. But we're mainly interested in the organic product, so you make this, which is what's called an N-nitrosoamine. So this would be the nitroso. Okay, so not terribly synthetically useful, but this is an interesting molecule. It's an important molecule because N-nitrosoamines, so the N means the nitroso is on the nitrogen, right? So N-nitrosoamines are carcinogenic. So they are naturally occurring. You need some N-nitrosoamines, and your body naturally produces some N-nitrosoamines. So they're needed in small amounts, but in excess consumption, they can be a health hazard because they're carcinogenic. So this is significant because sodium nitrite is used as a preservative in meats all the time. So you look at a package of hot dogs and maybe you see sodium nitrite on the ingredient list because it's a preservative. So the significance B is when you grill meat, if you char it, well, the nitrite that's present can react with proteins to make N-nitrosoamines, so you can be making carcinogenic compounds. And so that's particularly bad, I guess, if you eat that every single day, then certainly that would be a health hazard. But in limited quantities, probably not so much of an issue. But if you're barbecuing out every single meal, that could be an issue. Could be a health hazard. Okay, so N-nitrosoamines, synthetically useful, but they're more useful if you make them from primary amines, and particularly if you use arylamines, because the nitrosoamines that's formed can react further to make what's called a diazonium compound. So this will be an example. So if we take benzene, you know how to put nitro on benzene, right? That recipe is HNO3, H2SO4, so do a nitration. So we looked at that in chapter 17, and then if you want to reduce the nitro to the amine, we looked at that in this chapter. So you could H2 and palladium or lithium aluminum hydride would reduce the nitro to the amine. And then once you have the amine, you can react it with NaNO2 and HCl, and that would make the N-nitrosoamine. But if it's a primary amine, it won't stop there. It'll keep reacting. So we'll go through the mechanism, what's going to happen next. So once you make the N-nitrosoamine, it's going to keep reacting with HCl. So the oxygen will be protonated. And we're going to take this, so that would make this compound, and we're going to draw a resonance structure now. So let's take a lone pair here, move them down to make a nitrogen-nitrogen double bond, and move pi electrons on the oxygen to make a lone pair. So now we have this, and then let's lose a hydrogen from nitrogen. So those 2 electrons in the NH bond become a lone pair on nitrogen. And then let's basically repeat this process. So we're going to protonate the oxygen again. Oops, wrong way. So now we have a water molecule, so a good leaving group, and so a water molecule leaves. And we're going to take this lone pair make a nitrogen triple bond, lose a water molecule, and now you have a diazonium salt. So nitrogen's now positive. What's the negative? The negative would be the Cl minus that you lost in this step. So that's a diazonium salt, and they're usually not isolated because they are very reactive. Right? Why are they so reactive? Because you have a N2 group, a nitrogen that can leave us nitrogen gas, and of course nitrogen gas is extremely stable. Right, so this could leave us N2 gas. So basically, any nucleophile, a variety of nucleophiles can be used to substitute for N2. So you typically don't isolate it, because as long as you keep it in solution, and this is usually done cold, so maybe ice temperature, then the diazonium can be managed. But if you tried to isolate that, heat it up, it could be potentially explosive because of the nitrogen gas coming off. Okay, so synthetically how you can use that. So if you have water and you just start heating that solution up, then water can displace the diazonium and you can make a phenol. So basically nucleophile comes in, kicks off the diazonium. In this case, Cn minus is a nucleophile. So Cn can come in and kick off the diazonium, or bromide. So this is another way to put bromine on the ring. So now you've seen two ways to put bromine on the ring. So you could take benzene with Br2 and FeBr3, so back to chapter 17. Or if you made the diazonium, you could put bromine on that way. But this is the only way we looked at to put Cn on a ring. Or if iodide your nucleophile, then iodide can come in and kick off the diazonium. Or if you use BF4, so this is basically a source of F minus. So BF4, and then heat that up, then basically F minus will come in and displace the diazonium. So you can put a fluorine on the ring. Or if you wanted to get rid of the diazonium, then you can react it with hypophosphorus acid. And that will substitute the diazonium for hydrogen. So basically you got rid of the diazonium at that point. Or you can use the diazonium in electrophilic aromatic substitution. So if we took that and reacted it with phenol, well, if you remember, this is an OP director. So we could take so if we reacted that with phenol, we can take these electrons and make a bond to here. And these electrons become a lone pair on nitrogen. So now that carbon's electron deficient, and so it would tend to substitute at the para position and not the ortho position for steric reasons. Okay, so you've lost aromaticity at this point. If you remember the mechanism for electrophilic aromatic substitution, now you lose a hydrogen where the substitution occurred at and remake your benzene ring. And now you have this. So you substituted the diazonium at the para position of an OP director. So that's another example of that. So if we started with this molecule, and so that aromatic amine with NaNO2 and HCl is going to make the diazonium. And now if we react that with another aromatic molecule where this is an OP director, then that will do the substitution of the diazonium at the para position and make this molecule, which is a dye. This is called methyl orange. So this has color. Right? Why does it have color? Well, it has lots of double bonds in conjugation, right? It's got the lone pair plus the 3 double bonds in benzene, plus that pi bond, plus these double bonds, plus these double bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9 double bonds in conjugation plus the lone pair. So that's enough for it to absorb UV vis radiation in the visible region of the spectrum, so the molecule has color. Okay, so that's the reactions out of this chapter. So now let's apply that to some synthesis problems. So start with benzene. How do you make 1,3,5-tribromobenzene? So you know how to put bromine on the ring. So could you just do that reaction 3 times? And the answer is no. Why not? Is because that is an OP director. So how are you going to get them meta to each other? So this synthesis is a little bit tricky because we put something on the benzene ring to direct things to where we want them to go, and then we take it off. So it's hidden from you. So the way you would do the synthesis, so put nitro on the benzene ring, and then reduce that to aniline. So that's an OP director, and it's highly activating. So now we can do the bromination. Probably wouldn't even need the catalyst because NH2 is such an activating group. So it's an OP director, so that wants to put the bromine here, here, and here. 1, 3, 5 with respect to each other, which is what you want. So you just do 3 equivalents of Br2, put 3 bromines on. NH2 is highly activating, so that's that would be an easy reaction to do. And so now you need to get rid of the NH2. How do you do that? NaNO2 HCl, you make the diazonium. And then you take the diazonium off. So with H3PO2, right? Okay, so in this case, you've put a directing group on the ring to direct things where you want them to go, and then you took it off by utilizing the diazonium salt. Okay, so if we wanted to make this metachloroaniline, so this could be a tricky synthesis as well because that's an OP director. And that's an OP director. So how do you get them meta to each other? Well, the way you would do this is HNO3. So you would put a nitro on the benzene ring, and the nitro is a meta director. So now would be a good time to put the chlorine on because you would get it in the right spot. And so now you just need to convert the NH2 to the amine, and you can do that with H2 and palladium, right? Or lithium aluminum hydride. Okay, if you wanted to make this meta chloroiodobenzene, same issue as you have 2 OP directors. You want to get them meta to each other. So here we're going to use the diazonium again. But you know that's the only way to get the iodine on the ring anyway, so that's a clue that you needed to do a diazonium at some point. So put the nitro on the ring and then put the chlorine on. So to utilize the meta-directing property of the nitro. Right, and then convert the nitro to amine. And then convert the amine to the diazonium using sodium nitrite, NaNO2 and HCl. And then you can replace the diazonium with potassium iodide. And now you've got the molecule synthesized. Okay, one more synthesis problem for you. So if we wanted to start with benzene and make this molecule, so no, we have not seen a reaction that will just make this bond for you and put all of that group on there, so we need to do this stepwise. So we could have made this if we had this ketone. And we had this amine by reacting with H+, H2, and palladium, right? So that was a reaction that we covered in this chapter. That would make the imine, and then you get a H2 across the carbon-oxygen double bond. And you could make that ketone from benzene by doing a Friedel-Crafts acylation. Okay, so just a two-step synthesis in that case. Okay, so lastly in this chapter, I just wanted to show you a few examples of amines that are very important in biological chemistry. So just so that you see some of the relevance of this material. So this molecule is lysine. So it's got 2 amines in it, right? So that's an amino acid. This molecule is histamine, which has 3 amines in it. So histamine, of course, is if you have allergies and you take an antihistamine, you would be taking an antihistamine to try to reverse the effects of histamine, the allergy response that's happening. This molecule is dopamine. It's a neurotransmitter, serotonin. Obviously in brain chemistry, huge significance. So a lot of amines have stimulant properties to them, right? This molecule is epinephrine or adrenaline. Nicotine is an amine. Cocaine is an amine. Again, many amines have stimulant properties to them. Okay, so that's it for chapter 19. We'll stop there.